And so I know I said we were going to talk about this in the coming video, vector functions of constant length, but I'm just going to tell you the definition, and then we're going to do two examples that I think will help you more with your homework, because I think this kind of makes sense visually. So basically, when we are tracking a particle, P, moving along a curve which is on the surface of a sphere centered at the origin. So since this is a sphere, no matter where that position vector r of t is pointing out, it's going to be pointing out that full radius, right, of the sphere. So it's always going to have a constant length. And so whenever we know that that position vector's length isn't changing, what we can say is that if my position vector r is differentiable vector of t and the length of r is constant, something that we will know is that r and its derivative, which is the velocity vector, which is tangent to the point at that curve, those are always going to be equal to 0 when I dot product them. And that's because they're always going to be perpendicular. We can also show that in the converse, that if we know this is equal to 0, this dot product, r times its derivative, then we would know that that position vector is constant. But I think visually it makes sense. No matter where I draw this, if I were to draw that vector out to this point, and then I looked at drawing that tangent vector, these are always going to meet at a right angle. And if they're perpendicular, their dot product is going to be equal to 0. All right, so let's do two examples. Our first example, for this example, we're going to find the parametric equations for the line that's tangent to the given curve at the parameter value t equals 1. So our position vector, or our vector valued function, r of t, is equal to natural log of t times the I vector plus t minus 1 over t minus 2 times the j vector plus t times the natural log of t times the k vector. So as we know, a tangent line to a smooth curved vector value function is the line passing through the points. And then it's also parallel to the velocity function, because that velocity vector is going to be tangent to the position vector. So essentially, we're dealing with t equals 1 here. We know we're going to pass through the point f of 1, g of 1, h of 1, and that we're going to be parallel to the vector v of 1. So essentially we just need a point and a slope. So I'm going to plug 1 in to all of my parametric components for x, y, and z. So my point, the natural log of 1 is 0. If I plug 1 in here, 1 minus 1 is 0 over negative 1. I get 0. And 1 times the natural log of 1, that's 1 times 0, or 0. So there's my point. And then my slope is going to be the derivative evaluated at 1. So my derivative here, v of t, well, the natural log of t is 1 over t, derivative times I, plus the derivative of t minus 1 over t minus 2. We use our quotient rule for differentiation. We end up with 3 over the quantity t plus 2 squared, and that would be times my j vector, plus the derivative of t times the natural log of t. We have to use the product rule for that derivative, and we end up with the natural log of t plus 1 k. Evaluating this at t sub 0 equals 1, v of 1, 1 over 1, that gives me 1i, plus, I'm going to get 1/3 j, and then plus The natural log of 1 is 0, plus 1 is, we have 1k. So at this point, using our rules for the parametric equations that represent this line, my x equation is going to be the 0x value. We'll have plus 1t. My y equation is again going to be my 0y value plus 1/3 t. And my z equation is going to be 0 plus my 1t for my k value. So we can simplify this. We've got x equals t, y equals 1/3 t, and z equals t. So these are the three parametric equations which represent the tangent line at that point, 0, 0, 0, which occurs at t equals 1. Let's look at one more example. In this last example in our section of videos here, we're going to find the values of t so that the tangent line to the curve, this position curve, contains this given point. So the points 2, -5, -3, our position vector is given by -t times I plus t squared times j plus the natural log of t times k. So what we're going to do is we're going to determine a point of tangency. And I'm going to say let t equal some a value. Let that be where our point of tangency is occurring. So I can evaluate my function at a, and the r vector evaluated at a is -a times the I vector plus a squared times the j vector plus the natural log of a times the k vector. Now, a direction vector can be determined by the velocity or the derivative of this position vector r. So direction vector is going to be r prime of a. And so this is going to give us essentially the slope of the tangent line. So taking the derivative of a is -1, so I have negative I vector plus 2a times my j vector, and then the derivative of natural log a, I'll have plus 1/a times my k vector. So now using my point of tangency, which will come from this vector, plus my direction vector, my derivative vector, I can write my parametric equations for the line. So my parametric equations, I'm going to have x equals -a minus 1, and we would normally say t, but we already have a t in this problem, so I'm going to use another variable, q. We'll have that y equals a squared plus 2a t, or again q, and then z equals the natural log of a plus 1/a q. So at this point, we were given x, y, and z. X, y, and z, 2, -5, and -3. So we are just going to need to solve a system of equations. So really we have 2 equals -a minus q. My y value is -5, so -5 equals a squared plus 2aq, and minus 3 equals the natural log of a plus q/a. So we need to solve this system equation. We want to solve to find a, and that's going to be the value of a for Q in this case, where the tangent point occurs. Occurs at time Q. So I'll get my Q in there. All right, and Q is just representing time. So the easiest thing for me to do would be to use substitution method. I'm going to isolate Q, and that means that Q is going to be negative A minus 2. So I'll come over here and I'll say, we know that Q is negative A minus 2. And I can take that and plug that into my negative 5 equation. So now I have negative 5 equals a squared plus 2a times negative a minus 2. So simplifying this, negative 5 equals a squared minus 2a squared minus 4a. Negative 5 equals negative a squared minus 4a, or rather a squared plus 4a minus 5 equals 0. Factoring this, I would get a plus 5, a minus 1 equals 0, and that gives me, this is going to occur at a equals negative 5 or positive 1. And we'll get the same solution if we do negative 3 equals the natural log of a plus q over a, which was our other equation. And I remember I said q was going to be equal to negative a minus 2. If we plug that in there and do some algebra, this is also going to provide a equals 1. So now remember what a was. We said a, coming up here, t equals a is going to represent our point of tangency. So those values of t, where the tangent line is going to contain this given point, well, that's going to occur at t equals 1. And so again, at t equals 1, that's the value of t, where the tangent line to the curve contains this point. So that curve is passing through that point and then having the tangent line at that specific moment. So I hope that kind of helps you think about it a little more algebraically. I wanted to do some more examples in here for us. As always, email me if you have any questions.